For that, what you need to do, you have to go for the electron microscopy. So the first we start with the eye, then we went for the light microscopy, and the later is the electron microscopy. That if we'll talk about in terms of like how much resolution, good resolution we can get. If we'll talk about in light microscopy, maximum you will get around to be 100 nanometer if you have a good microscopy. Okay. In the mostly microscopic which we have most of the time in our labs, that will give you a resolution of 1 micron. But if we'll talk about SCM or scanning electron microscopy and as well as transmission electron microscopy, there you have a resolution of zero point 0.1 nanometer. So just imagine, with the help of AI, you will not able to see a proper thickness of your hair. Now we are talking about in the nanometers. So how these things will be able to, how we are able to see these things. So this we'll talk about later. So first, as I explained, first is the light microscopy. So what is the light microscopy? Light microscopy, as the name suggests, light, mean to say your source is optical light. You are going to use a light as your source of generator, like source of your material, which is basically light is bombarded on your sample surface, and in reflection you are going to get, yeah, you are going to get your microstructure. So what are the different parts of your light microscopy? One is the body tube, another is nose piece, low power, medium power, high power, stage clips, diaphragm, light source, eyepiece and arm, and the stage. And then the fines just and the base. So this is basically about the one light microscopy, which is having a different phases like body tube, nose piece, low power, medium power. The basic funda of his here is, one is the eyepiece and another is basically your sample pieces, which is basically low power or high power depending how much you are going to use it. And another is a basically coarse adjustment you mostly have, and the fire for the fine adjustment you have. In some of the cases, your stage is basically opposite of your eyepiece. So this is different eyepiece. A light microscopy, I'm just going to show you. Some of those you have coarse adjustment for roughing, focusing, and as well as you have different tissue sections are there, specimen tissue sections. So to consider it, or to with the help of those condenser lens, you have also condenser lens, which is basically focus on the light to give you better resolution. So these are the different types of the light, different parts of the light microscopy. Can image change your view? Definitely will change. So I'll give you two different like one sample, which is basically uh, examined with the help of light microscopy as well as the scanning electron microscopy. So these are the, like this is uses under light microscopy. If you can see, the resolution was quite bad. So you're not able to judge how fine pore system are there in the system. But if you are going to use the electron microscopy, you can see the fine microscopic porous system, which is basically differentiate. Now the question is why it is happening. This is the reason behind it. This is a resolution. If you can resolve this issue, this is not okay, because both of the microscopic parts is basically lie on each other. If the both are overlapping on each other, the resolution is going to be bad. So to resolve this, you need to put it in different aspects, like you need to use a proper aperture size. So this is another example of optical microscopic image of nanofibers. You can see you are basically seeing different layers but not able to clarifying it. But when these same nanofibers use in scanning electron microscopy, you can visualize the fibers quite clearly. So this is the difference. And definitely the if how you are image changing or you are visualizing the image, this will definitely change your image view or your mechanism. So for that, you need to judge your microscopic quite easily. Let's take two examples. If you are using light microscopy and another is an electron microscopy, what is the carrier? Carrier is basically which rays or which source you are going to use. The first in it, you are going to use light as an electron as a source, but in electron microscopy, you are going to use electrons as a source. So what is the wavelength of those things? For the light, we basically use 400 to 800 nanometers, but in electron microscopy, we are using basically around to 0.0037 nanometer wavelength. So this is the difference. Because of this difference, you are able to generate high resolved image. And this will, now the question is, what media can be used? Like, can we use, like in light microscopy, we don't require any, we don't
So the voice is not coming.
Hello.
Hello. Hi, sir. Sir, so you're not audible, sir.
Now audible, sir.
Now audible, sir.
स्टार्टिंग से ऑडिबल नहीं था या इन बिटवीन?
सर इन बिटवीन चला गया था थोड़ा सा, सर.
Okay, somebody muted me. Okay, so should I start from the beginning?
No, sir.
Sir. When you are talking about wavelength of light and electron microscopy, when 200 nanometer and 0.037 on that time it is also.
Okay.
Yes, sir.
Okay. So the second is the medium. Like what type of media can be used? Like in light microscopy, you can use air. Like you need not to require any vacuum media. But in electron microscopy, you required vacuum because when the electron is going to be generated, you want the maximum bombardment on your sample, and there should be no interaction of electrons with the outside media. So that's why we need vacuum. Then the third is lenses. Lenses. So in a light microscopy, we required only glass lenses, but here we need electromagnetic lenses. As you know, electrons generate two types of nature. It is a particle as a wave. So to converge those things, we need electromagnetic. Okay. So then there is what is the basic output we'll get with the help of these microscopy. The basic funda or basic reasons for how it is going to work. Light microscopy is basically working on the reflection as well as absorption and the phase change. But contrast is in electron microscopy, it is basically scattering and the diffraction. So diffraction is basically base reason how we are going scattering, as well as diffraction is basically used for this output of your the electron microscopy. And another, the main difference between light microscopy and electron microscopy is how we are going to align those our electromagnetic lens or a glass lens. In light microscopy, we basically aligned with the help of mechanical alignment. But in terms of electron microscopy, you have to do all this electronically. because you are basically going to align a fine electrons. So that cannot be done mechanically. For that, you need electromechanical lens. And the depth of field and the information which we're going to get from the light microscopy is basically mass density distribution. But in electron, we'll get the chemical composition, mass density distribution, as well as crystallographic texture, like how your grains are oriented, how what type of texture is there in your material that can be easily identified with the help of electron microscopy. So these are the basic information we're going to get with the help of electron as well as a light microscopy. So how this working is going to be worked, how the working of microscoping is going to take in place. The first, I already told you about the light microscopy. The source is light. Light source is there. Then you have a condenser lens. Then in between you have an objective lens. Then your eyepiece, which is near to your eyes, from where you are going to visualize it, and the image viewed. Nowadays, basically, we also use computers, CPUs to see those type of images. We don't require much eyepiece nowadays, but in the old tabletop microscopy, light microscopy, you used to have eyepiece lens also there. The second is scanning, and the third is the transmission electron microscopy. In this scanning electron microscopy, your basic funda is like how you are going to the electron is going to bombard it on your sample. They are basically diffract, and you are with the help of detector you are going to capture those data, and then you are going to visualize it. Okay, but in transmission electron microscopy, the out this detector is not on your like here the detector is at particular angle, like diffraction is going to be taken place. Here the transmission is basic thing, like that your detector is just beyond your just below of your specimen. So whatever data you are going to capture, you are going to capture from the transmission, and because of this thing, the resolution is going to be improved a lot. So you are going to get around to 0.1 nanometer scale data with the help of transmission electron microscopy. So the how the working in the construction contains, like what is the electron gun, what is demagnification system, scan unit, focusing unit, as well as detecting unit. Because we have different type of detectors, or we used to called as attachments, like how the EDS, WDS, EBSD, those things are going to be worked. So first we'll start with the electron gun. In normal, we are talking about the electron gun. Then we have an anode, condenser lens, as well as we have a scanning coils. The scanning coils is used to convert your electron in a particular on your sample. It basically help us to convert a single beam on and try to drop or bombard all of your electron on near to yours on your sample. And then the object lens. So if we'll talk about what are the different type of SEM and how it is going to be functioned. So as I already explained, to observe objectives which we are not resolvable by our naked eye. So resolution, its ability to see too closely placed object as a discrete structures. So this one, like if you'll see, this is a basically with the help of scanning electron microscopy, we are this image was taken during I was walking in Thapar. So there we used to see we able to see this image. The first we me and one of my operator was there. We are trying to see the ant head in normal way, but we are not able to resolve it because our depth of focus was not good. So after playing with different parameters, this is the image which we captured. So this is all about how you are playing with your electron microscopy. This is basically improve the depth of focus. We have easily capture and you can see the resolution of your microscopy. So now these are the different microscopy which we had here. So if we'll talk about different electron guns, which I just asked earlier, one is first the tungsten filament. Okay, the tungsten filament, it's basically used in old microscopy, which is having a tungsten filament at the above. The and the it usually had a working life of 100 to 200 hours, depending how like how good you are using and on which aperture size you are using, and parallelly what type of samples you are really using. So that is basically tungsten filament. Then we have one more. This is also one of the oldest method, that is LAB6, lab 6 single crystal, which is having a carbons header rod and a ceramic on the base. So this is having a better resolution as comparison to tungsten. That recently or last 20 years we had a new electron gun which is have FIG, field emission gun. What is the difference between field emission gun and the tungsten? It is also having a tungsten filament, but the tungsten filament is now coated with ZRO and a single crystal ZRO. Meaning to say all the like ZRO film, whatever it is on the surface, it is basically covered with a single crystal, one single grain of ZRO is coated on it. So that can be easily, that basically improved the resolution. How? We are going to see later. So this is a basic difference between all three electron guns. The maximum current which we can go in tungsten is 1000, LAB6 500, and FEC Schottky is around to be 300. Brightness, if you can see, it's changed from 2500 times in field emission gun. Energy spread is quite high in tungsten. Because of that, we are not able to resolve this issue, resolve the features quite appropriately. But in fact, the resolution is quite good. Another is the spot size. In the source spot size, we are talking about in microns. In fact, it is in nanometer. So the spot size is basically key factor when you are resolving the fine features. If one of your spot size is greater than the key features, then you are not able to resolve it. Let's suppose you want to see your uh, your hairpin or your hair, but like spot size which you are using is the size is greater than your hair, then two hairs are combined in one single point. So you are not able to resolve the thickness of one single hair. So this is the way the spot size play an important role. The same now come with the vacuum. In tungsten filament, we need not to require go for the higher vacuum. We can go in 10 raised to the power minus 3. In LAB6, we need 10 raised to the power minus 5. In fact, you need required 10 raised to the power minus 7. So the temperature is basically in FEC Schottky, it's around to be 1800. From 2700, so you should reduce it with the 1800. So lifetime, I already told you 100 to 200 hours. 60 if you are not using it in a proper manner. 60 to 200 in LAB6, it's 1000. In Schottky, it's more than 2000. Nowadays, we have a good spec source are there that go around to be 10,000 also. So definitely all these features is basically increase your price. So in normalized price, like if we'll talk about tungsten, if it is cost rupee 1 rupee, then peg is going to cost you around to be 100 rupees. So this is the difference between pricing of one normal. So now we'll start about the short key emission. So this is the two different like chambers, or we can say in that is work. First is the source, where your source is going to be located. It is going to be located above, at the point of this. And here the vacuum should be required 10 raised to the power minus 9. Another is your chamber, where your sample is going to be inserted. So here the uh, vacuum is going to be around its 10 raised to the power minus 5. So this is the two different chambers are there for normal fake gun. These mostly you will, but wherever you go for your scannings, like for testing, you can see these type of electron microscopy. So this is your basically source, which will tungsten, as well as there is a ZRO coating, which basically improve your resolution. So this is the basic SEM which I already showed you. Condenser lens, then scanning coils, objective lens, and how you are basically capturing your image. So then it will have a SCM setup. What type of different information now we can capture with from that? So there are n number of information we can capture. Like let's suppose one uh, electron is bombarded on your sample. You can get primary as well as secondary electrons. Secondary electrons is the electrons which basically interact your surface and give you the topographical information about how your microstructure look like. But sometimes you want to see what type of different phases are there. For that you need a backscattered electrons. So for that the interaction of your electrons with your sample should be a deeper. So for that, there you will get about the phase contrast as well as topographical information. Both the information you can get with the help of backscattered electrons. And later we'll talk about what type of interaction it will going to be there. It's going to be elastic or inelastic, that we are going to see later. Okay. Then parallelly, like let's suppose there are interaction are going to be taken place. There should be energy transfer as well as energy loss will be there. So those energy is basically used to identify what type of chemical composition you have in your sample. So, and there should be some X-ray which is going to be like emitted during those interaction. Those X-ray could be uh, characteristics as well as continuous. Those also we'll see, as well as we are going to get the Auger electrons, which is basically surface sensitive, and it will give more compositional information as comparison to others. So later I'll tell you how with the help of WDS, your sample is work like a small XRD system. So we'll see later. So first, we'll see, as I told you, first is a secondary electron microscopy. Secondary electrons, which is basically interacted your sample and reflect back. So these are the primary electrons which bombarded electrons on your sample, interacted and come back. These are inelastic collision. Inelastic collision means there should be some energy transfer will be there. Okay. When one electron strike with the another electron, there will be some one electron came out your shell, and that there will be some energy loss will be there. So this energy loss is called as inelastic collision. Okay. But it is having a low energy because it is basically interacting with your sample surface. But when we'll talk about the elastic collision, here you are going to get more deeper information. And here the elastic collision mean to say overall energy loss will be less or negligible. So those are called as elastic collision, in which you are going to get the appropriate information about your atomic numbers. Like if you want to see the phase contrast, you can easily captured with the help of backscattered electrons. So let's suppose you have a sample which is having two different phases, and you want to identify, you want to know what type of what is the phase fraction of one phase to another phase. Then you have to go for the backscattered diffraction method. So scanned electron will not going to give you that much good information. For that, you need to get a backscattered electron information. So that will give you more appropriate idea about the phase distribution inside your material. So let's talk about this is your sample. Now we have a primary beam which interacted with your sample. So this type of shape will occur when the interaction of electrons will be there with your specimen. The first, if you can see, it's near to the surface only. The scanned electrons will form. Then the second, the backscatter. If you see, the difference between them is high. So there is more deeper information you are going to get from your specimen. Now this shape or this size is basically depend like how much voltage you are going to use. So this is how much voltage you are going to say you are using it a 5 kV, 20 kV and 30 kV. So then according to that your 1 micron, 2 micron, the depth of the interaction volume is going to be changed. So that I'll also show you later. And then this is a characteristic X-ray. These characteristic X-ray is basically used for the identification of elemental composition. Like if you want to use, there are two ways. One is to use it as an energy. How much energy is you lost? According to that, we can calculate energy dispersion spectroscopy. We'll get energy versus curve, and we will get to know ki, like what type of chemical compositions are there, like how much percentage of iron is there, copper is there, or those type of information we are going to get. But if you want quality wise, then you need to use a WDS, like wave number. So you are going to use directly X-rays. So there your sample is work like WDS is like a, your sample is work like a small XRD system where your X-ray source is your specimen and detector is trying to identify what type of X-ray it is emitting. So there the Bragg's law is going to work. 2D sine theta is equal to n lambda. With the help of that, we'll able to find out. Now we know the lambda, we know the n, so we can easily find out d. So that d is basically give about the what type of element or what type of atom is there in your side your material. So this is the way how it is going to be used. Then there is a specimen current. Why it is important? Like if your sample is conductive, it is quite easy to detect. Like sometimes we are working on a ceramic glass, then that's a problem. If your sample is not conductive, then you need to make your sample a conductive so that the like whatever you will see, electron is coming, bombarded on your sample and reflecting back or diffracting back. Okay. But if your sample is non-conductive, mean to say he is all he is basically what he is going to do. He is going to capture all the electrons. He is not going to emit it. Mean to say there is no reflection back or diffraction. Uh, all the electrons, whatever we are bombarding it, is going to capture or taking all the electrons within the sample itself. So there will be no emitting of the electrons will not be there. So then you are not going to get any information. For that, you need to make your sample conductive. For that, you can use a different type of coatings. Like you can use a gold coating, you can use a carbon coating or platinum, whatever you want to use it depending. And the coating thickness is also going to play an important role. If you are making your samples too much thick coated, you are not going to get proper information from your sample. You are going to get information only of the coating. So those things also should be taken care. Then the Auger electron. These are the electron. This is also from the surface information we are going to get with the help of OJ electrons, but this is more sensitive your sample surface. So for that, you need to create your sample preparation should be in a proper appropriate. So as well as there is Brem's X-rays will be there. So this basically used for the radiology applications. So this one will need to take care, and there is cathodoluminescence light there. So these are the basic information which we get when electron is basically bombarded on your sample. So scanning action of electron beam across specimen surface will be like this. So these are the basic, like let's suppose your electrons is bombarded. So OJ electron, if you can see, it's basically from the surface. So this is the shape which we are going to get. Okay. So the depth of this penetration is basically depending how much voltage you are basically using, as well as the aperture size and your accelerating voltage. What is the benefit of accelerating voltage? We are also going to see later. Okay. So energy distribution of electron signal. If we're talking about the secondary electrons, it's basically 0 to 50 electron volt. But in talk about backscattered, it is higher than 2 kV or 3 kV. So this will give you more appropriate uh, phase fraction and those kind of stuff. For that, you need a proper interaction in surface interaction volume of your electron with your specimen. For that, you need a higher voltage. So these are the various components. These are the secondary electron detectors. In the backscattered detectors is near to your pole piece itself. And this is your sample. So electron beam typically has an energy range from zero point 0.5 kV to 40 kV. It is focused one or two condenser lens with a spot size of around to be 5 nanometer. And it scans in a raster function. Raster function means to say it is basically taking pixel by pixel raster way. So then what is that I already discussed earlier? How the spot size play an important role and what is the correct focus and how the correct estimation is going to take place. So let's suppose you are basically taking an image which is having a 442 to 3094 scanning lines. Okay, these are your features. This is a spot size. One spot size is not basically overlapping the other. So the features you are basically resolved it quite good. But in another way, if your spot size is basically overlapping the other spot size, the resolution is going to be reduced. So the overall resolution is not proper in that manner. So the overall, like if resolution is not good, the image which you are going to get is not focused. You are not going to get proper information from your sample. So this is another example estimation. Like let's suppose your sample is focused like this one, but the estimation is not proper. Like mean to say your image is tilted in particular direction, and you are not able to see your features properly. It is basically elongated in one particular direction. If you'll see, it is in this image, it is basically elongated in y direction. Here it is opposite in that direction. But this is the proper pore size. If you want to calculate the pore size, we'll not able to calculate with the help of this one. But this is the proper image where you can get the appropriate pore size in your material. So these are the images which is under focus. This is image which is under focus again. This is focus, but stimulation is not there. To correct all these things, this is the output of your video. So this is the proper appropriate way to capture your image. So effect of spot size. So one is the aperture size. So mm, if you are basically changing the aperture size, so you are basically changing the large. If you are using the large aperture, your resolution is going to be decreased, as well as your X-ray. You are going to get more information from with the help of your X-ray. So your elemental analysis is going to be improved, but there should be a optimum working distance which can be used for analyzing that data. If your aperture size is small, then you are going to get greeny image as well as high resolution and the better depth of field. Now we'll talk about the working distance. If your working distance is small, your depth of field is small, that will improve your resolution. Mean to say you are going to resolve fine features with a small working distance. But if you are going to increase your working distance, then depth of field will not going to work. And as the depth of field is greater, the resolution is not going to be good, and you are basically going to get uh, one or other feature is going to be get overlapped with each other, and you are not going to get appropriate information from your sample. The question is, like, let's take an example. Like, if you have a special guest, how you are going to uh, how you are going to welcoming and what type of different things you are going to give in front of him. So for that you need a proper you need to give a proper time, you need to analyze it, you need to function it in a proper way. So proper evaluation will be need to be there. For that you need to find out what type of aperture size, what type of spot size, you have to work it out, and that also change from your sample to sample. So this is basically good evolution. You are going to give him ample of things. So then if you will take about this example, okay. So what you are able to see, this is a fine sheet which is having a pore structure which will taken at 5 kV. Just see how the voltage is going to evolve. 5 kV, you're not able to see a thin film. It's like no Mr. India, you are basically seeing something is missing from here. But when I'm just changing the voltage from 5 kV to 2 kV, you are able to see there will be a fine layer, thin film was there. But what about the surface morphology of the thin layer? Till now, we are not able to see it. So, mean to say, we need to resolve this, or we need to change the voltage a bit lower side. So, what we did, we again reduce the voltage. So, if you can see now, the film is quite clear, and there is too much roughness is there inside your film. So, this is way how it is work. So, you need to play with your microscopy. You need to find out which is the appropriate voltage you have to use it. So another is the tilt correction. So first, I'll give you the example of how the voltage play an important role. Then the second, how the tilt correction is going to take place. So if you see this, what you are able to see, this is a fine structure which is having a porous, nothing is there. But when the tilt correction is taken place, you'll see the gold particles onto the surface. So this is the difference of the tilt correction. These are the images which we took during my stay in IITB. So before tilt correction and after tilt correction, how it is going to work. So this is the uh, inside chamber of your electron microscopy. So this is your pole piece from which electron beam is basically bombarded on your sample. This is backscattered electron detector. Then there is uh, large field detector is there for the ESAM. ESAM is basically environment scanning electron microscopy. Like in mostly metallic or conductive samples, we use uh, normal electron microscopy, which is having a as I showed you earlier, there are two chambers. One is for the your specimen, another is for your electron gun. So the specimen chamber we used to have a pressure around to be 10 raised to the power 10 raised to the power minus 5 bar millibar. But in this electrons scanning electron micro environment scanning electron microscopy, the specimen chamber or pressure is too low because the sample whatever we are using those are non-conductive. So for the non-conductive samples, if we are not using the coating, then you need to reduce the pressure of your pressure of your chamber. So another is the collimator is there, and as well as this is basically scanning secondary electron detector. As well as near to this, there should be a EDS detector will be there. Energy dispersive spectroscopy, which is basically used to find out the chemical composition of your sample. So one high vacuum is required, then definitely there will be low vacuum, and then the ESEM. So which mode to use? For that, you need to know what type of samples you have and what type of information you want to capture from your sample. Solution. Like we are going to take different samples. Let's suppose you are having a metals, alloys, or metallic materials from atomic number 4 to 92. So you can use normal electron microscopy, high vacuum electron microscopy. Like if you have a chemically stable but all poor electrical conductor, ceramic, rocks, geological sample, minerals, particles. So, and as well as you have some polymers, some synthetic organic polymers, biological polymers, biological organisms, as well as wet and liquid samples. So these are the, like suppose we categorize in 6 different categories. So metallics, we can go for the high vacuum also. And if you have a samples which is basically wet or liquid samples, either you have to go for environment electron microscopy, ESAM, environment scanning electron microscopy, where the vacuum pressure is quite low. There you have to use, or the biological sample also can be used in those kind of stuff. There you are going to get appropriate information about your samples. So polymers you can use in high vacuum as well as low vacuum, depending like how much like coating you are basically placing on your sample. So these are the things which you have to take in care while using your SEM, like which type of SEM you can use it. So these are the different tools which usually we used to have with our SEM. And these are the tools which is basically used during sample preparation also. So let's suppose you have a powder samples, and so how those powder sample can be mounted. So like if you have a primary metals sport, you can 12 mm, 25 mm, any p-tilt holder, groove type holder can be used. Then secondary sports is basically TM grid, glass slides, metal foil, wrapping, embedding. But in powder samples, you need to use it in a proper way. So for that, you need to take your powder, put it in dissolve it in particular solution in which your powder will not react with your solution, so that it will as it is in, like you can use it ethanol, methanol, isopropanol, and dry the solution put it in air or your heating chamber, dry it and put it on the carbon tape or copper tape, and then coat it on the powder, and then you can use it to see how the microstructure of your powder can be look. So first, take clean it, alcohol, use powder free natural gloves, mount it, then take butter paper and put it the sample on it, and then dry it. Because like when you are putting powder, try to put powder samples on low vacuum or ESAM. If you don't have that option, you want to put it in high vacuum, then try to use a hand blower kind of stuff, so that whatever the loose particle of powders you have, it can be easily removed. Okay, so the particles which are interact basically attached with your copper tape or carbon tape, only those will be used for seeing the microstructure part. Okay, so these things you need to taken care during the during scanning electron microscopy test. Otherwise, it will going to affect your apertures. It will contaminate your aperture, and after every 6 months or 1 year, you have need to change those aperture. So these should be taken care during the use of that. Basically, you need to put it good adhesive particles. The loose particle should be removed. So then the second is that there is a new detectors usually came, DBS basically, for backscattered structures, in which you can use a different shells A, B, C, D, which used to KLM and shells which you have in your atomic structure. So you can use a different shells to look at your microstructure. So these shells is basically again going to change according to your atomic number of your microscope sample. So let's suppose if this is the same sample, you are basically seeing it in different shells. If you are seeing, D is basically giving us more appropriate information about your microstructure. Or other example I'll going to give. This one is if you are going to see, this one is basically taken with the help of A. So if you can see the B, you can easily identify the two different phases are there. And with the help of this, you can easily identify the volume fraction or a weight fraction of your secondary phase inside your material. So this is the benefit which we can take during the usage of this. So that earlier also I talked about the coating. For non-metallic sample, this is the main point. The how good coating, how like appropriate coating you are using on your sample. The wrong way of coating is like you are putting a thick coating on your sample. Mostly coating when we use when we have a polymer or a non-metallic surface, then we are going to use it to make the material conductive. But if you are using coating which is having a higher thickness, the interaction volume of your electron will not to be able to reach to your sample surface. Then you are not going to get your information from your sample. You are going to get information only from your coating. So this coating, one, there should be a uniform coating and the thickness should be appropriate. It should not be less or more. So that is basically depend like how like what type of samples you are using. So let's suppose you have a polymer sample. So the 30-second coating will be enough for your to get good information. And coatings are usually like you can use gold, carbon, platinum, depending if what type of samples you have. And the topographic resolution is limited by thickness of the metal core and the secondary electron range. So those should be taken care. So one is a beam declaration is basically talking about the accelerating voltage. Sometimes we used accelerating voltage, but accelerating voltage is going to give, it's going to basically improve the resolution of your sample. By applying VR, it basically improve your resolution of your sample and give more appropriate information from your sample. So that can be improved by just improving the accelerating voltage. So these are the parameters which usually we play. Uh, from one is the sport size. I already gave you the example. Spot size will always be lower than your feature size. If it is more, then the both of the things, then two spots will be overlap with each other. You are not able to resolve the fine information from that. Then the second is sharpness. So sharpness is basically depend on your accelerating voltage as well as the working distance. So for that also you need to take care what type of accelerating voltage you have to use. Then probe current, secondary electron, as well as the backscattered electrons. You need to take care of your backscattered electrons also. Then depth of field, charging. Charging is basically we usually see in polymers. So when we'll talk about the charging, let's suppose you have a having a higher aperture size, higher aperture size, higher aperture size. So you need to having uh, high charging or beam damage will be there. That should be in case of polymers mostly it will be taken. So for that you need to. So these are the examples. Decrease the electron beam intensity, shorten the exposure time. Let's suppose you are basically capturing image in 20 second or 30 second. Reduce it till 10 second. Image large scanning area with low magnification to capturing the image at like 40,000 or 50,000. Try to take that image at 10,000 with a high resolution, and then control the thickness of your coating metals. Coating that is also going to be taken place. Now, what is EDS? EDS is that I already informed you that's energy dispersive spectroscopy. So how much like X-ray going to be produced during bombardment of electrons from your samples? Those can be used to find out what type of elements are present inside your material. So every solid state techniques with a unique artifacts. So these are the basically structure of your EDS. This is one of the oldest EDS, which is basically having a cryo state. That during our PS, during my PSU, we used to have we used to put liquid nitrogen to for the cryo state, and then the we used to have a collimator assembly, electron tape, window, and crystal. Those kind of stuffs will be there. So this is basically used to find out the elemental analysis. So for SCM slash EDS, if you want to use the electrons needed from zero point 0.5 to 30 kV, the signals is like X-ray. The resolution is going to be changed from 1 micron to nowadays it is even improved till around to be 10 nanometer and so on. So detection limit is around to be 1000 ppm. So WDS it's around to be again 1 micron. So if you are basically improving your lateral resolution, 5 to 9 nanometer is going to be there in AEM and EDS. So if you are having XPS kind of stuff, then you have 1,000 micron resolution, and depth of resolution is around to be lateral resolution is 1,000 micron, and depth of resolution is around to be 3 nanometers. So that's why mostly like people want to see what type of uh, in which state your material is element is, like it's in +2 or +3. Then we people you mostly used to go for XPS kind of stuff. So other than that, there is atom probe microscopy, and micro IR is also there. which is basically used for the this type of characterization. So these are the different type of X-ray, characteristic X-ray and continuum X-rays. And one is the experimental. So if we'll talk about the X-ray, we'll talk about K alpha and X-ray L. These are the different X-ray which basically K beta is basically emitted during your interaction of your electron with your sample. So these are the curves which basically plot, and these X-ray lines are used to see what type of elements are present in your. This is basically give you qualitative use X-ray energy to identify elements, and quantitatively use integrated peak intensity to determine amount of elements, how much particular like 2% is there, 3% is there. Those kind of analysis we can use with the help of these analysis. So this all worked on the Moore's law. So what it say ki energy, how much energy is basically reduced is basically going to taken care with the help of atomic number of your samples. And C1 and C2 are two constants which directly give you the elemental analysis with the help of this law. So if the energy is given in K, L, M, N line is measured, then the atomic number of the element producing the line can be determined. So this is the uh, uh, easy way to calculate how what type of element is present in your material. So normally we used in X-ray from 15 to 20 kV for EDS analysis. So these are the light elements which can will emit X-ray of the K series only, and intermediate basically emit X-ray of L series, and heavy M and L M series or L and M series. So these are the ways to calculate the X-ray. So there EDS, so what type of elemental analysis with the help of energy dispersion. So dead time and real time processing time counts rate are basically what how much lifetime is there plus the dead time. So that is basically depend on the your clock time. So processing time is mostly we used to have 15 like let's suppose you have a 15 microsecond time needed to process the X-ray event. But overall it depends like how much CPS counts you are going to get from your samples, like how much out uh, X-ray is emitting from your samples, that is basically defined. So X-ray EDS process only one photon at a time. So X-ray scattering to close in the time are thrown away to prevent recording photons at incorrect energy. So you need to taken care of the artifacts which basically see in your sample. So let's suppose you have a 3000 CPS. So around to be 20 to 30% is your dead time in that. So you need to take care of that. So the detect so X-ray measurement is basically effect of detectors processing time. So however your processing time is nowadays, the detectors are quite fast. So the processing time is basically quite less. So lower dead time and higher acquisition rate is going to be give you worse resolution. For that you need a higher dead time and lower acquisition rate give you the best resolution of your sample. So detector performance is basically going to see how the energy resolution is there, uh, charge collection is there, detector window, detector contamination like uh, count rate कितना होगा आपका, energy calibration, the maximum through output कैसा होगा. Those are the things which will can be taken, which should be taken care during the EDS analysis. So these are the some examples like when you are getting wrong information from your uh, wrong information from your EDS detector. So these should be taken care while you are capturing it. So you need to use the fluorescence peaks or those kind of stuff internal fluorescence, photons generated in dead layer and detected in active region. So those things should be taken care when you are collecting your data from your ADS. In qualitative analysis of the silicates, there are some combination of element of K alpha peaks that falls too close to a K alpha peaks of elements possible. As so, the during the detection of your element, you can't rely on one single peak. You need to see like how the secondary peak is overlapping. So how these artifacts are looked back. So these are the escape peaks. System peaks are will be there. So you need to see all those kind of stuff. So these uh, these are the secondary electrons which is basically talk about. So because as we are talking about backscattered is basically 1/3 of your volume interaction. In secondary, we are talking about 100 angstrom. So in backscattered, we are talking about 1/3 of your volume. So X-ray emission, 2/3 of the volume. Like let's suppose now we are talking about the influence of accelerating voltage. Let's suppose you have a 30 kV, 20 kV, 15, 5 kV, 1 kV, and 50 kV. So you can see the depth penetration. And this is I'm talking about an iron case because I mostly worked during my PhD and others. I worked on steel. So this I'm talking about an iron case only. So the depth of penetration, like electron penetration is around to be 3 micron when we are talking about 30 kV. But in 15 kV, it is around to be 1 micron. And in 5 kV, it is around to be 0.15 micron. So 1 kV, it is around to be 0.01 micron. So 35 Armstrong only 500 volts we'll talk about. So these are the low Z and high Z differentiation. Like if you are having a low atomic number, so how your oval shape look like the interaction volume, and if you are have a high shape, it's going to convert it in spherical, not as comparison to oval. So the accelerating voltage, spot size, tilt angle, those are basically going to change at low kV and high kV. So these are some different examples how your elements worked or see at different electron volts and what type of the depth of penetration will be there at different time. So these are the what effect quantitative analysis, K ratio, atomic number, accelerating voltage, absorption, fluorescence, atomic matrix. So these are the different parameters which affected during your interaction volume time. So the K ratio, it basically intensity versus the intensity of your atomic number or depend करेगा, and then the atomic number and accelerating voltage is again like how much what type of element you are talking about. According to that, you need to change your accelerating voltage. So it is 1.5 to 10 times exciting energy and 2 times at the highest peak energy. So these are the things which you need to take care. So low overall voltage means a small properly excited peak or poor statical quantity in the so X-ray volume in your oval shape is going to be quite less. So this is again is going to be taken basically on your accelerating voltage. So let's suppose just taking it angle like at EDS detector when we are placing it at 35-degree, how much X-ray can be captured with the help of this. So when we are changing the base angle, so you are getting more information. So sample position is extremely important. Working distance is important. Optimum sample position, field of view of index detector, as well as if we're talking about the sample working distance, it should be 9 to 12 mm. To 9 to 12 around. If you are working above 12, then more inhomogeneous illumination of the field we, uh, we are going to work. So we are not going to get a proper information in terms of EDS. So your field of view will be increased. So overall, you are not going to get proper information. So 9 to 12 mm is basically appropriate or optimum value for your EDS detector. And exact, it will depend at what angle you are placing your EDS detector. So which elements are present? It can be used, collect as many X count possible, scan over a large area, no, avoid a single point, at least capture 2 or 3 points. Use more than one peak to confirm that I already told you. So one single peak is not going to give you exact information. So we need at least 2 to 3 peaks to confirm those points. As well as we need the bulk target, like proper standards on the sides, and uh, collected on another SCM and then corrected for the geometry settings should be there, and rough surface will not be there, so those should be taken care. So these are the some points which is basically talk about the combined two peaks. Then you need to resolve it, or overlap peaks should be taken care. You need to remove those peaks and try to find out how what type of different element should be present in there. So these are basically artifacts. These are some examples which I'm basically giving you to find out the what type of artifacts are there inside your samples. So how you can resolve those artifacts. So uh, like overall, like spectral artifacts or poor counting settings, basically low counts, noisy. System will identify noise, identify find out the solution, give a long acquisition time, high count will be there, then you are going to get a proper information from your sample. So the K ratio, which we will talk about earlier, is basically intensity element sample versus intensity of pure element. So that will give you the K ratio. The proper K ratio should be required to identify what type of elements is there in your sample. So you can see like these are the X-rays or which you basically used for the EDS detectors when your electrons bombarded on your sample. So these are the absorption of X-rays. So you need to prepare your sample. So sample roughness is basically play an important role. The surface or sample preparation should be there. So that's why the coating as well, when we'll talk about uniform coating as well as in metallic, sample surface uh, preparation should be proper. Like sample preparation should be in proper way. So uh, there are angles at the highest and the lowest peak are basically give you the example. So if you have any questions, you can ask. This is all from my side. And this is the first for the first, and the second is going, we'll talk about new research, which is basically going to be with the help of these electron microscopy, X-rays, what maximum new research, what we can do with the help of these high-end characterization techniques. So if you have any question, you can ask. You are free to ask.
Can I ask you, sir?
Yeah, sure.
Sir, it's really very nice presentation. In fact, lots of things to understand, and I have lots of questions. But I'm just asking some one of the question only. Actually, I want to see the video again of this your presentation. It's quite interesting. Actually, can I able to get this video link or which is being present? Either it is being present on YouTube or somewhere else.
Yes, sir. Yes, sir. After this session, tomorrow we will post this link in this WhatsApp group, and you can watch the video there.
Okay, sir. My question is that you are given about the primary beam of electrons, primary electrons, backscatter electrons, secondary electrons, and Auger electrons. Okay,
Yeah.
sir. In your backscatter electrons, you're telling about that this being utilized for atomic number and topographical information, and
Yes.
for the secondary electrons also that are the topographical information. Can you and
Yes.
this electrons are for surface sensitive information. Can you please elaborate this thing little more so that I can able to understand, or with some example? Can you please tell me?
Let's suppose okay, we'll take an example like that. Like if you want to see the grain structure of your material, you can just go for the secondary electrons. Okay. Like let's suppose you have a steel, which is basically having a, which is okay, not steel is it? Okay. Just take an example of steel, which is having a two different phases. Okay. And then you just want to see the grain structure of your sample. So for that, you can go for the secondary electrons. Okay. You want to see like what is the grain size there, how the grains look. So that can be done with the help of secondary electrons. But if you want to see what type of phases are there, like either there is a single phase system is there or a two phase is there, then you have to go for the backscattered. So what's the difference is going to be taken place in secondary electrons? You have an inelastic collision. Okay, so that the information whatever you are going to get, you are going to get from the surface. The interaction volume with respect to bombarded electrons from your specimen is quite low. So you are going to information getting the information from the surface. But when you are going to get the backscattered electrons, the interaction volume from your samples specimen is going to be high. So you are going to get more deeper information. So according to the like atomic number, you are going to get different phase contrast. Let's suppose you are having a one is having a higher atomic number, another is having a lower atomic number. So both the phases will going to give different contrast and brightness. So according to that, you are going to get different information. Or I'll show you one of those. I think I'll show you one of the more good image of that. Hmm. See, if you want to see these type of phase contrast, so you are going to get with the help of backscatter mode only. If you want to see the two different phases with two different colors, in this is not two different phases. Let's suppose base will having a one phase, another upside is having a different phase, and both of them will give you a two different contrast. So that can be done with the help of only backscattered mode only. Not with you are not going to get that much good information with the help of secondary. And the OJ is basically as the interaction volume is also quite low as comparison to secondary electron. So this is more surface sensitive. So sample preparation is going to be taken quite a vital role in that. So you need to prepare your sample properly. And the another lecture which I am going to have at 7:50 or so, there I'll show you some of the good images of that, like how the backscattered and secondary electron work. So there also you can understand those points.
Thank you, sir. Quite clear. So will you talk about TM also in your next lecture?
Yeah, TM also.
Thank you, sir. Thank you very much. Thank you very much.
That is mostly on EBSD and TM.
Thank you, sir.
Any other question from participants?
Sir, good evening, sir.
Good evening.
Sir, the same question also I have noted in the previous participant asked the question. And further extend some question is, what is the necessity of the images captured from secondary electron and backside electron? That means called bright field image and dark field image in the microscope. What is the observe information from the image system of SEM microscopy? And another one question, sir, why the magnetic material not supposed to use for testing the same microscopy? And what is the difference between the TEM and tunneling electron microscope, transmission electron microscope, and the difference between tunneling electron microscope? So please give me your explanation, sir, little more.
Okay, the first, the second question which you talk about, I forgot. The second question you talked about, why can't we use the electromagnetic magnetic samples in your scanning electron microscopy? As you see the structure of your electrons, you have electrons like you have electromagnetic lens are there. So if you are using magnetic samples, there will be chances that those uh, magnetic lens are there, if you can see it. Okay. So if you are using your magnetic samples, there will be a chance it can create, or it can like basically uh, create a problem with your specimen as well as its chamber. Okay. The second is because of the nature of your electrons, there will be chances there will like beam drift will be there in magnetic samples a lot. To focus on that particular point will not be easy for the magnetic samples. For that, we basically avoid to use magnetic samples in your uh, SCM. Okay, so there are different methods which we can use to uh, like to use magnetic sample in SCM. There are different methods earlier, like you can use low vacuum mode, or these type of different methods will be there, or environmental mode.
S-
There we can might be use some magnetic samples, or you have to stick, or you can stick the magnetic sample to make a different type of holder and tighten it with the help of screw, and those type of stuffs you can do to use the magnetic sample in your electron gun, scanning electron microscopy. Okay. And then you talk about the difference between SEM and TEM. Uh, the
No,
TM is
no, sir,
basic.
no, sir. TM and tunneling electron microscope.
Okay. TEM and tunneling electron microscopy. And another which you asked first question, that is
It's a first question, sir. Bright field image and dark field image of same. Uh,
Okay. The first is the like in transmission electron microscopy, whatever output we are going to get in the detectors, which is basically lying behind and under your samples. So the resolution and those things is going to be different in tunneling, as well as you are basically using the tunneling gun in that part. So the resolution in tunneling as well as transmission is going to be different. So if you are in the bright field and dark field, if we'll talk about that, basically depend on the diffraction pattern. Like in mostly, if we'll talk about in EBSD, we used bright field uh, Kikuchi patterns. In the bright field, Kikuchi pattern will be there, dark field will be there. That depends like according to your atomic number and the how much the d spacing will be there. According to that, we are use it in bright field and dark field of your samples. So those can be that's why I'm telling you. In my second lecture, I'll show you the EBSD and those stuff. So there will be more clear to you how what is the difference between those aspects.
sir, if you use any magnetic type of material, can you apply
Uh,
any?
I think
Uh,
magnet
sir,
for example,
magnetic.
where you need to use any magnetic tape for testing the morphology, if you apply any etching or any other coating on the material before you testing this sample, sir, if
No,
you anything, sir.
like if we'll talk about like used to
If you
analyze the
need to use,
CRGO steel. And CRGO steel, that is also like some of the magnetic properties is there, CRGO steel. Okay, so what we used to do, we used to make a different kind of holder, which is in which this sample is tightened with the help of screw. Okay, so that is tightened it in a proper way, and we used to have use the STM in low vacuum mode, so that the magnetic effects will be quite less. Okay, so those type of stuff we used to do during using the magnetic lens in the steel sample which I used. But in the powders that I never use, so I can't comment on that.
Yes, sir. Thank you, sir. Thank you.
so thank you very much, Dr. Hitesh, for this beautiful session, well explained session. And we will meet again at after 20 minutes break, sir.
Yeah, after 20 25 minutes.
Okay, so we will meet at 8 p.m. sharp.
Yeah, 8 p.m.
Okay, sir. Thank you very much. All the participants, please rejoin us at 8 p.m. Thank you. Thank you very much.
Our 100+ diverse programs span multiple disciplines. Where innovation meets tradition stands one of India's premier education institutions, Chandigarh Group of Colleges, Mohali. With a vision to empower youth and transform them into globally competitive professionals, CGC Mohali has consistently set new benchmarks in education. Our 100+ diverse programs span multiple disciplines. We offer an education that is not only comprehensive but also deeply rooted in skill development and industry relevance. Through advanced programs and state-of-the-art facilities, CGC provides its students with the tools to succeed in today's fast-evolving world. Our engineering and management degrees are designed to meet the demands of the industry with cutting-edge curriculum and experiential learning. Computer applications and paramedical sciences courses give students the expertise to excel in the digital world and healthcare sector. And with our programs in fashion designing, law, commerce and journalism, we nurture the creative, analytical and practical skills necessary for leadership. With our Innovation and Skill Development Center, we foster the next generation of innovators and problem solvers. It's a hub where ideas take shape and the brightest minds come together to solve real-world challenges. Our business incubator, Venture Nest, provides budding entrepreneurs with the resources, mentorship and support to turn their dreams into successful ventures. CGC Mohali's commitment to global education is reflected in its international collaboration with over 150 universities across 50+ nations. These partnerships allow our students to engage in global research initiatives, exchange programs, and build a network that spans continents. And for those who aspire to reach greater heights, CGC offers the Josh Scholarship, a unique initiative that provides scholarships worth up to 25 crores. It is more than just financial support. It is a pathway to empower the next generation of leaders to follow their dreams. With over 1,200+ companies visiting our campus, CGC students consistently receive top-tier offers. In fact, the highest package offered was a staggering 53 LPA. With over 10,000+ job offers, CGC is where career dreams come true. At CGC, we believe in the power of inspiration. Over the years, we have hosted some of India's biggest names in business entertainment.
Today I just finished a pep talk with the students of CGC Janjeri
and sports. Celebrities from all walks of life have graced our campus, sharing their stories and wisdom with our students. Through initiatives like National Cadet Corps and National Service Scheme, students actively engage in nation-building activities. Whether it is serving communities, participating in sports competitions, or showcasing their talent at cultural festivals, CGC students are always at the forefront of making a difference. CGC Mohali also stands strong in its social commitment. With Naya Savera Foundation, we ensure that our students are not only trained for their careers but also learn the importance of giving back to society. At CGC Mohali, we believe that education is not just about earning a degree, it is about building character, fostering innovation, and developing skills that empower students to take on the challenges of tomorrow. But don't just take our word for it. CGC has built a community of proud alumni who have achieved remarkable success in industries across the globe. Join us and be a part of a legacy that goes beyond education, a legacy of excellence, innovation, and endless possibilities. CGC Mohali, where your journey to success begins.
again welcome Dr. Hitesh. Next session. So welcome again, sir.
Hello.
Hello,
Yes,
sir.
sir.
Hello. Can we start?
Yes, sir. Yes.
Okay. Okay. Give me a minute. Okay. Welcome you all again. So the second session, which I already discussed with you. So in this, I'm going to show you some of the results, which basically taken with the help of these high-end characterization techniques. So it basically divided into two parts. First is basically some of my PhD work, which I did during my stay in IIT Bombay, and the second, which that is on the 3D printing or additive manufacturing, during my stay in Thapar. So those so those two different categories I use. So to give you the overview of different materials, in which we are going to see how the steel is basically used, and how steel is going, how the steel microstructure can be taken care. Good steel microstructure we can capture with the help of scanning electron microscopy or EBSD, and then through TEM, and TM only in the bright field, not in the dark field imaging. And then the second part we'll talk about the additive manufacturing, in which polymer as well as metal additive manufacturing also with the help of SLM should be is generated, and then how to characterize those things. So first I'll just give you the because this research part is basically talk about the oxidation behavior, how the microstructure aspect is going to affect the uh, oxidation behavior or oxidation kinetic of your steel base material. Okay, so people will talk about the filling width ratio when it is less than 1, near to 1, and greater than 2. So if it is near to 1, then it is good. You are going to form a good oxide layer, and which is more oxidation resistance. So overall, it is a good. So then the second, like also people talk about how the cation diffusion, anion diffusion will be there in oxidation kinetics. So to start that, we'll talk about how the role of microstructure is going to affect the oxidation kinetic. So in role of microstructure, we choose that time we choose two different steel. One is the interfacial free steel. If people may know, interfacial free steel is basically a structure which is having interfacial free atoms in ppm. like carbon, nitrogen. Those are basically major interfacial atoms which sit in the unit cell of iron in interfacial sites, and that basically used to improve some of the mechanical behavior of your material, definitely. So if it is less than if those things are in ppm, so material used to have a single phase, that is ferritic, bcc only. bct will not be possible without interfacial. So to perform like martensite, either you have an interfacial atom in your material, or you need to deform it at a higher rate. So one is that one we took, another is a eutectoid. Eutectoid is a basically two-phase material which is having a ferrite and cementite, like lamella structure. Like when I used to teach in my class, I used to say those are sitting in a boy girl ratio kind of stuff. So that is a lamella structure. One one to one boy, one girl, one boy, one girl kind of stuff. If it is there, that is called as lamella structure. One ferrite phase is there, then cementite, then again ferrite, then cementite. If those kind of structure is there, that is called as perletic structure. That for that we use the eutectoid steel. So usually in eutectoid steel we used to have 100% perletic structure. So this is I'll just show you. This is a structure of about perletic material. So this is again a different type of perletic. So we thought of let's change the morphology of perletic structure and see the how the oxidation is going to take in place. So to change the morphology, we use thermomechanical processing. Like thermomechanical mean to say we divide thermomechanical in two parts, basically thermal plus mechanical. We are basically deforming it as well as we are changing the heating rate, cooling rate. Like you are basically deforming as well as applying deformation means to say mechanical deforming, as well as thermal mean to say applying heat also. The combination of both of those things will going to change the microstructure of your material. So if you see like first the question arise how to capture those morphology. Let's suppose you change it, how to capture that thing. So for that, as already explained you, we need to go for the scanning electron microscopy in last lecture. So the scanning electron microscopy, you have to go for the either secondary electrons or a backscattered electron. So if you want to see the two different phases, you have to go for the backscattered mode. So in the last, I somebody has asked me, so what is the difference between secondary and backscattered? In backscattered, you can easily see two different colors of two different phases. So okay, so this is the clear example of perletic structure. So to identify it, we use like SCM, and we took some good images with the help of backscattered mode. And these alignment means to say, like when I'm talking about 31% aligned, mean to say out of 10, three perletic colonies. Let's suppose this is one perlite colony. Out of 10, three perlite colony are aligned in y-axis direction. That is basically perpendicular. If we'll talk about this is the perpendicular direction. Out of 10, three colonies are aligned. But if we talk about 66, you can see this is a perpendicular direction. Out of 10, 6 colonies are aligned in perletic direction. So we just change the alignment of perletic colonies. So what we observe, this experiment took place in TGA, thermogravimetric analysis. With the help of TGA, what we observe, the oxidation kinetics change. So the question arises why it is happening. What would be the reason behind it? To find out that, we captured the EBSD. We we want to see like how the oxide structure is, and parallelly to find out how the oxide structure is and how the phase distribution is there in that particular oxide. In iron, basically there are three. If we'll talk about in normal, like not like if you are heating it in the presence of air, oxygen, there are three different phases can be possible. One is the hematite, Fe2O3, then Fe3O4 magnetite, then FeO, woostite. Okay, so these three different phases can be present. So how this distribution is there? To find out that with the help of SCM, that can be only possible if we'll go for the EBSD, that is electron backscatter diffraction. In last lecture, we'll talk about only secondary electron microscopy. Backscattered mode couldn't able to add it because of the time limitation. So in backscattered mode, we tilted it at 70-degree sample, and the backscatter detector will be there, which is going to capture all the electrons, which is basically scattering uh, from your sample, and it's going to capture with the help of detector. And the normally it's angle at 65 to 75, but 70 is the optimized one. So what do you observe? The overall distribution of FeO, Fe3O4 and Fe2O3 is more or less same, but when we are having a 31% aligned, there is a small porous structure is there. Mean to say, the oxide scale, whatever is forming on your surface, is not completely intact. So why it is, that question arises. So here is one more point. If like some of you want or is presently working on coatings, so the best way to analyze the coating is to see the cross section of your coating. If you want to analyze like if you want to analyze like how much thickness of the coating will be generated by different experiments of yours, so that best way is to see the cross section and then try to analyze it at 3, 4 or 5 different places, and then take out the average. So that will give you an appropriate idea how much thickness of coating can be formed and how you can improve it. Okay, so the overall that can be so we observe there is a small porous structure is there. To find out that, we thought of these are the colonies which is having a very fine perlite, very fine lamella structure. So let's create a microstructure which is having a coarse perlitic colonies. We created with the help of laboratory scale. So in laboratory scale, what we did, we controlled the cooling rate. What we did, we slow down the cooling. So that gives us enough time for the cementites to saturate and then the ferrite. So if you can see, these are the like around to be 7 to 8, around to be 1 micron lamellas, there is 1 micron differences there between one ferrite to another, one cementite to another cementite. So this is called as coarse perlitic colonies. Okay, so then we did the EBSD to find out the phase fractions of the perlitic. So and then what we tried, we took 2 different colonies or 3 different colonies or 4 different colonies to find out how the oxide scale look on those particular samples. What we observe, when we are having colonies which is more aligned to the wire axis direction, the stresses are quite high, or when these are quite high, those stresses are like if you like, let's suppose those are morely aligned to the wire axis direction, the stresses are quite low at the cementite phase. But another, when they are not aligned in a particular direction, the stresses are quite high. So because of this stress difference, there might be the chances there will be relaxation is there. Because of that, we are getting the crack inside your oxide scale. So to find out or to confirm that, we calculate the orientation relationship between ferrite and cementite. There are two old literature like 50s and 60s literature is there which talk about those things. There are two different orientation relationship is there. One is Ishachi, another is the Begaski, which talk about the OR between ferrite and cementite. So what we are observe when we are deviating from orientation, those orientation relationship, so the stresses are quite high on those particular colonies. So at the end, what we find out first, if you want to find out the stresses, local stresses, interface crystallography is going to play an important role. And those stresses is basically directly impact the stability of your oxide scale which is forming. So if you want to form a good oxide scale or a scale which is more adherent to your surface, then you need to form a good orientation relationship between your ferrite and the cementite oxide. So from here, I'm moving toward the second part in which, and this paper was published during my PhD in Scripta Metalla. So in the second part, we'll talk about, like I'm going to talk about interfacial free steel. So interfacial free steel, as I already told you, there will be chances only like one phase is present, that is ferrite. So if you want to change the morphology, you can only change the texture of your material or a grain size. Okay, so in this, we try to change the texture without hampering the grain size. Definitely in starting we get the different grain size, and the later on we compare one to one with the same grain size with different texture. So again, with the help of thermomechanical, like with the playing with the cold rolling and annealing parameters, we generated a material which is having which is having a grain size of around to be 56, and the texture ND parallel to 111, or we used to call in our daily studies like gamma texture, which is basically good for formability. If you in mechanical, if you want to improve the ductility of your material, you can change the gamma texture of your material. Your material is going to have a good ductility. You can take an example like if you have a car sheet, just cut it and do the microscopy of those sheet, which is basically you make to use the door or upper body of your car, is going to have definitely gamma texture in your material. So without that, steel is not having that much good formability. In the same grade, if you create the gamma texture, your formability is going to be good. So what we did, we tried to create a gamma texture 0.17 to 0.75 with the same grain size, as well as we also created in between different gamma fraction 0.1 to 2.1 to 0.66. This is also confirmed with the help of X-ray bulk texture measurement. And so after that, what we did, we oxidized. First, we did some trials, and after it, reading some literature, and that we'll get to know around 300 degrees Celsius, the first oxide which is going to be formed on a steel substrate is going to be magnetite. So we optimize one cycle for 300 degrees Celsius for some appropriate time, oxidized both the samples. So what we observe, ND parallel to 11 grains was the first grains which is basically oxidizing in our material. So to confirm that, we have a same materials which is having same grain size material which is having 0.75, and what we observe, the all blue grains in raw terminology, I can say that blue grain is basically talking about the gamma fiber grains. The gamma fiber grains are totally vanished. So you can see. So the first formation which is having on the surface is basically gamma fiber texture is going to oxidize first. This is confirmed. Then let's, okay, now find out the oxidation rate, or how much the weight gain is there from different, is it like uniform for different texture also. So we try to find out, and it's a linear progression. If you can see, there is a, like, if you are increasing the gamma fiber, the oxidation rate is increasing. So that is also confirmed, another point. So this also, we did Raman spectroscopy on those grains. So as literature suggested, the first oxide grains which is forming was magnetite Fe3O4. That is also confirmed with the Raman. So we thought of, like, let's find out how magnetite look. But it's mean, is one single grain of magnetite is basically covered with the one single grain of ferrite. Mean to say, if single grain of ferrite was there, was it covered with the one single grain of magnetite? Or there are n number of small grains are there which will be covered with one single grain of ferrite. So to confirm that, we increase the temperature a bit higher side, 500, and what we observe, one single grain of ferrite is basically covered with one single grain of magnetite. And parallelly, there is an orientation relationship is there. That is 45 degree 100. And if you can see, this is like around to be 300 400 nanometer fine scale, and this is the cross section of the grain. So you can see one single grain is basically covered with one single grain of magnetite. The blue color is basically ferrite, and the red color is basically magnetite. This is at 500 degrees Celsius. So, okay, we thought of, let's hit it above 570. So the question is, why 570? You can ask. The 570 is the temperature where the eutectoid transformation took place, where the Fe plus Fe3O4 is basically converted in FeO, oosterite. So, like, if you hit it above eutectoids transformation and cool it down, because reverse eutectoid will also be taken place. So are we going to get single grain covered with a single grain? No. Here we are going to get n number of small grains. This is magnetite because it's a reverse transform, eutectoid reaction will be there. Again, then FeO is again converted into Fe3O4 and Fe, but you will see n number of small grains. This is called as reverse eutectoid, and shape memory. Sometimes it's a texture memory that would also called as. So why it is happening, to find out, we calculate the Voronez's strain as well as the dislocation density inside your material. So one ferrite substrate, another is a magnetite. So what we observe, when we are having a gamma fiber grain, the overall the dislocations inside the density in Fe3O4 grains are quite high. That basically leading towards a material to form more oxide scale. Because of this reason, we are getting more oxide surface. As well as this is also confirmed with the help of Raman stresses. Raman stresses are basically hydrostatic stresses, which is also calculated with the help of this Raman peak deviation, which is basically formed. So to confirm that, we also tried one, there is a homoepitaxy is there. Another, there is a pseudoepitaxy, which is basically above 570, and substrate orientation is basically determines the dislocation and stresses in the oxide film, which is basically clear. So to confirm that, we also calculate the defect density. This defect density is basically calculated with the help of Mott-Schottky analysis. And this is the one of the way to calculate the oxide thickness at different nanometers. As well as we also, with the help of XPS, we also calculate the fraction of magnetite and hematite in the oxide scale. Like, let's suppose you oxidize it for the longer run and try to find out how much ferrite formation and hematite formation is there, how much hematite as well as how much magnetite formation in the oxide scale is there. So that also will be calculated with the help of this one. So what we observe, when we having a material which is having more textured one, gamma fiber, we are having more magnetite structure. And as it's well known, the magnetite structure is basically spinel structure, which is having a more porous structure, which is basically more, if aligned towards the oxidation, or it's basically more porous, so there will be chances to interaction of more oxygen with the substrate and the substrate with the oxygen, and form more and more oxide. But if we'll talk about a material which is having a random structure, there is a Fe2O3 hematite is there, that is a corundum structure, that is more complex. So more complex structure, the porosity is less, and this will improve the oxidation kinetics. So if you have a material which is having a gamma fiber, the material is more oxidized, oxidation prone. But in other way, material is having less oxidation prone. So this is also confirmed with the help of defect density as well as the volume fraction of oxide. With this is XPS also confirmed with the uh, data which we calculated with the help of XRD. XRD is basically give you the phase fraction also, as well as texture result stress analysis also. Phase fraction we use like high score to do that analysis. And this paper also published during my PhD part. So it is in Acta Metalla. So from here I am moving towards the third part, that is role of alloy chemistry. So in earlier we already saw how the substrate microstructure is going to play an important. So in this we thought of, okay, fine, now the substrate microstructure is playing. So let's change the chemical composition, or let's add some copper, phosphorus, and the later chromium. So are they going to change the oxidation kinetics? If yes, then how? So in this we try to produce, or we able to produce uh, binary alloys which is having uh, copper percentage from 0.5 to 3.5, and then phosphorus 0.01 to 0.1. And in this paper we will only talk about the binary alloys. We didn't move towards the secondary alloys. And as we already know from our earlier work, texture play an important role. To normalize that one, we try to make the material which is having a uniform texture. So if you see, so here I only included the copper texture, copper material microstructure. So if you can see, the overall texture is more or less same in both the in all the materials. And if we'll talk about the volume fraction, ND parallel to 111, it is more or less same in phosphorus as well as in copper material. So second, in mostly in copper addition in phosphorus, it used to form some nanos, nano precipitates at the grain boundaries. So in that we'll also try to find out the formation of nano precipitate with the help of SCM and TM. So we got some good nanophase precipitates are the grain boundaries, which I showed you later part. So these SCM, it showed the uniform distribution of copper in throughout the matrix. There's not much inhomogeneity is not there. So overall alloy is homogenized throughout the material. So these are the XRD data which we also calculated from the which also later on help to find out the residual stress inside our material. So to confirm again later, we'll try to find out is there uh, homoepitaxy or pseudoepitaxy change by adding some alloying inside our material. So what we observe, there's no much changes are there in the epitaxial group, homoepitaxy or pseudoepitaxy of the. So there is again there is orientation relationship is there between ferrite and the magnetite grain, that is again 45 degree 100, and rate is also by increasing the copper content or the phosphorus content, we are getting a material which is a more oxidation resistance. So overall oxidation property of our material got improved. So to confirm that, we try to find out how why it is happening. We did some TM analysis on that, as well as some EBSD analysis and some chi scans. So chi scan is basically you are basically doing the EBSD. Same time you are calculating the capturing the EDS data from the same samples. So you can see near to the metal oxide interface, there is a one like layer of phosphorus is there. In copper case, we got the same oxide layer of copper. So which is basically the percentage of phosphorus is quite high in that particular fine layer. So this basically improving the oxidation resistance. It is more compact or adherent to the metal oxide surface, metal surface, which is basically improving the oxidation resistance. So we also find out the what we can say the oxide microstructure. It is basically you can see columnar growth structure is there in the magnetite grains, and there is some retained wustite is there, which do not uh, reverse Ryu-Tector transformation could not able to take place in that particular points. So and this is a ferrite surface. But when we are talking about the phosphorus and copper, again the formation of hematite is more, which is again as explained earlier. It's a columnar corundum structure, and this is a spinel structure. This corundum is again improving the oxidation resistance. Other than that, we are having a phosphorus rich or copper rich oxide layer near to the metal oxide interface, which is also again improving the oxidation resistance. So this is again we'll also try to find out how the dislocation structure is there inside the oxide metal interface or near to the oxide metal. So this is the bright field image which we took. The bright field image is basically capturing the normal image in the TEM. In the dark field, uh, we basically either tilt the beam or tilt the specimen. And mostly cases we tilt the specimen. We never trying to tilt the beam. So to align the beam again is a big task. So most of the cases we tilt the specimen and trying to align it one particular point, that is called as the dark field image. So in this we are basically taking the image in the bright field mode only. So this one we also calculated the dislocation density in last study. The same trying to find out with the Raman stresses. Again, those confirm that these are the improving as we are increasing the copper and the phosphorus content. So overall, the dislocation density go down as well as the Raman stresses go down. That improve the oxidation resistance of your material. So This paper was also published. This is an oxidation of metals. One journal is there. So this is also peer review journal. So this one also published in last year. So then we move towards the third part of my PhD work. For that is effect of chromium on oxidation resistance. So in this, we also make some binary alloys only, which is having a chromium content from 0 to 20. So as we already know the texture, so to remove the texture part, we prepared a material which is having more or less same texture. But what we observe, by increasing the chromium content, this is also well known because we are talking about the stainless steel, how the stainless steel improve the oxidation resistance. So this is also well known, but here we want to find out what is the basic mechanism, what chromium oxide is basically doing. Chromia, Cr2O3, is basically how it is improving the oxidation resistance. So the overall, basically when we are improving the increasing the chromium, overall oxidation resistance improve. So what we observe, like till 8 chromium there is a one single trend, and above 8 there is a one single trend is there. So we divided into two parts. One, choose the chemical composition. One is 8 chromium, another is 12, to see how those differences there. Another is a 16, to find out about from 12 to 16 how much variation is there. So this is again the image you took in backscatter mode. If you can see in backscatter mode, you can clearly visualize when this is a base, this is single phase, this is one single phase, another phase, and the last phase. There is a contrast difference between the present is there. So this is the benefit of taking image in the backscatter mode. So the first phase, which is to confirm that we did some Raman analysis on that particular oxide layer, which is having a resolution of around to be 1 micron. Uh, so what we observe, the first layer, which is basically from the first layer, which is basically next to the metal oxide, is basically having FeCr2O4, which is basically again a spinel structure. And the second, which is having a columnar structure, having, this is again confirmation of the columnar growth, is having Fe3O4 magnetite, again a spinel structure. And the last one, which is having a spinel corundum structure, that is hematite, Fe2O3. This is also confirmed with the help of X-ray. To confirm this, we also did EBSD analysis. So because it's a big oxide layer, like around to be 100 micron, so we did divide into three different regions and try to find out. And you can see how the columnar growths are taking place. One big single grain in the columnar. This happens during the solidifications. One growth solidification concepts will be there. So to confirm that, these things will confirm. Now to find out how the 12 chromium, the material which is having 12 chromium, how that will going to be look. So this is again the base material. If you can see, you can see the texture around, small texture difference, small different grain structure will be also there visible quite. Then there are two different layers are there. This one again, and this one. So to confirm that, it shows the FeCr2O4, as well as there is small peak of chromium oxide Cr2O3, which improved in case of 16 chromium. So this also confirmed with the X-ray and as well the EBSD. So by changing the chromium content, what we observe, we are getting different nature of oxide field. In phosphorus and copper, we are not getting much film differences there in the oxide scale. But in this, it's clearly visible. So we try to find out how with the help of WDS, because we want to calculate the like elemental analysis, we want to do the elemental analysis in more precise way. So for that we you go for the WDS. What we observe in 8 chromium, there is a sudden sharp change is there. It's stagnant and it went down. Chromium content is not there at till the oxide scale of 80-90 microns. But in 12 chromium and 16 chromium, the most oxide layer is having chromium content, which is basically proving how much Cr2O3 is there inside your material. And this is also captured, like we also try to find out the hardness of the different oxide layer. So what we observe when we are having a Cr2O3, the hardness of the oxide layer is quite high. And this also confirm with the help of Raman stresses. So what we thought of, let's find out the fracture toughness of the oxide film. So if you can see, this is your base material. This is a one single oxide layer, which is next to the metal oxide. In 8 chromium, it is basically mixture of uh, Fe3O4 or FeCr2O4. In in 12 chromium and 16 chromium, it's basically formation of Cr2O3. So you can find out the fracture toughness of your material. So what we observe, these this cantilevers are prepared with the help of FIB, focused ion beam. So we thin it or remove the oxide layers and only focus on the oxide layer which is next to the metal oxide interface, and create a cantilever which is having a length of 24 micron, and then with the help of nano indentation we deformed it. Basically it work as a point load and deformed it. So what we observe, by increasing the fracture toughness, the by increasing the chromium content, the fracture toughness of the oxide layer got improved, and this basically forming more adherent and the more oxidation resistance prone layer. So overall material is getting more oxidation resistant. So this paper is also got published in JALCOM, Journal of Alloy and Compounds. It's also peer reviewed journal. So uh, so overall, from an I can conclude it's basically synergy into metal oxide microstructure and no change in the oxide nature. Misfit across metal oxide interface determines the oxidation kinetics, which we observed in our second and the third part. And fracture toughness is basically changed as the nature of the oxide film got changed. So this is my work from till the IIT Bombay. From there, I move toward the next part, that is on additive manufacturing. As we are having less time, I'll try to conclude it as early as possible. So what is basically additive manufacturing? Basic purpose of additive manufacturing is first to design. Definitely, we can get like data for additive manufacturing from different aspects. In I'm just talking about SLM. We created our CAD design model, converted into STL format, then did some cross-sectional layers thinning, and then construct the model and clean and finish the model. This is the way how the additive manufacturing took place. So in metal additive, there are like powder bed fusion is there, direct energy deposition is there, and sheet lamination is there. So in this paper, I'm just showing you about the electron beam. Other than that, I also worked on fire feed and the powder feed system also during my other works. So as well as SLM also, selective laser melting also. So in this also, I'm just working on the EBM. I'm just showing you the EBM. So what is the basic problems we face during the additive manufacturing? One is the residual stress. Because the heterogeneity of your thermal gradient of your material, so or the difference in the or the optimization of not optimization of the scanning speed is basically form the residual stresses inside your material, and as well as these creates some porosity or it's different type of defects inside your material. So these are the some good literatures. We talk about this effect of various scanning strategy on porosity, as well as there not much literature which is present which talk about these, and people didn't talk about residual stress much till now. So how to resolve this? So that was our main focus when we start trying to work it out. And there is another, the build direction, you will going to get the columnar growth, elongated grains. So but this basically like increase the inhomogeneity in your material. So how to cope up those things? Those were the first part we thought of, to do some secondary processing like HIP plus heat treated. So those kind of stuffs to improve the or to decrease the inhomogeneity or to improve the homogeneity in your material. So this is again the some old literature which talk about the columnar grain morphology. You can see this long single grains, which is if you'll talk of this is if we this is talk of build direction. If you go to this other side, you will get small grains. So whatever you going to check like mechanical deformation in build direction and opposite to the build direction, there is a too much difference in homogeneity will be there. So origin of the columnar grain morphology, origin of anisotropy, grain growth direction depends upon the thermal gradient inside your material. So parallelly, when the columnar structure will be there, a texture difference also will be going to be there. So if you are going to change the build height, so you will going to see the difference in the texture content. So that texture content like build height also going to play an important role. So these are some good examples of the same. So if you can see, these are the defect density inside your material. So because of the build direction and other things. So fusion is also uh, going to play an important role. So our work was to EBM nickel based super alloy. We used iron 718 and try to find out like we took it in three samples. Like one is the as built, which is having more inhomogeneity. Then hip, like high deformation, hot static pressure deformation pressing we used to say at high temperature. Then hip plus heat treated. Like after hip, we did some heat treatments. So these are the different microstructures which we got observed. These are secondary electrons images. So if you can see this, these are not a backscatter, these are secondary electron images. So if you talk about in the contour direction, and this is the contour to H transition, and this is H. So you can see how the grain size distribution is too much inhomogeneity is there. You can, it is clearly visible. So near to that, there is like too much variation inside the material is there. So we also try to find out the grain morphology with the help of EBSD. So how the texture going? If you can see in the near to the contour at the end, there is like small grain structure is there. But when we are moving from the contour to H direction, the columnar structure is there. In H, again single structure is material is there. So we try to find out like because this is a clear example of seeing the same image in secondary mode and backscatter mode. If you see the secondary mode, you are not able to see any type of secondary phase or precipitates. But in backscattered mode, these are the clear example of precipitates. So we'll try to find out what type of precipitates are forming near to the grain boundaries. So what we observed, it's a gamma matrix, and as well as niobium carbides are there, which is present inside your material. So we also try to find out what is the distribution of there in the H and in the contour direction. So which is basically having intergranular gamma as well as intergranular, so, networking of both the things will be there. So the size of both are different. So we try to also find out the defects in terms of the volume. As built is having the higher defects. To minimize it, we did some HIP treatment, or try to lower it down, we did some HIP plus heat treated. So if you see in the contour direction, after HIP plus heat treated, it go down. So this is the effect of like like if you like, as we know, then there is too much inhomogeneity is there. To reduce the inhomogeneity, you need to go for the HIP plus heat treated. Or you, but you can say you need to go for the secondary processing after treatment. So this is also showing the microstructure difference from contour to H direction. Inhomogeneity is there. So but when we are moving towards to HIP plus heat treated, trying to reduce the inhomogeneity in both the cases. So these are the some good microstructures in which we are going to get some annealing twin. Twin basically, two type of twin structure will be there, mostly present inside a material. One is called as annealing, another is a deformation twin. So during deformation, if some twins forms, those are called as deformation twins. So these are basically anisotropy inside your material. So these basically shows how the microstructures look like, as well as a misorientation present inside your material. So what do you observe when we are giving the hot pressing, hot isostatic pressing, you are going to get more misorientation, but after heat treatment it is reduced at quite a higher level, and you are getting more homogenized structure. So this is again confirmed with the GAM and the GAUSS. GAUSS is basically called as grain orientation spread, that is also calculated with the help of. So, so this is again prove the. So we'll try to find out how much precipitate fraction is there in the contour as the H direction. So what we observe in heat plus heat treated, uh, uh, in H direction, niobium carbide precipitates will go lower, but in contour direction, again because our heating treatment, we are heating it at higher temperature, the formation of niobium precipitate is more. So in another one of another this another related paper, we tried to lower down the heat rate temperature, and there we also see the less fraction of niobium carbides. So this is again formation of gamma prime and double prime micro precipitates inside the material, and some see different precipitate structure inside the material. So roads. So we also try to find out like how the high hardness is basically varying from as built to hip or hip plus heat treated. So because as I already showed, like niobium carbide structure increase, so because of that the hardness got improved. So these are the different ways to improve the hardness. So overall the contour region exhibit more heterogeneity grain morphology, and the H is having more columnar structure, which is basically more the textured one, and the post-treated material, which is having more delta phase, and both as built and post-treated have gamma prime and gamma double prime phase, which is contained in the edge and the contour in both the, and similar hardness for the both the regions we observe. So this is the last part, which is basically talking about the polymer screws. So in this, we try to prepare the polymer-based orthopedic cortical screws. So in this, I think one of my collaborator in TIT, because he's more uh, because till now I never worked on biomedical applications. So he's Dr. Vishal is there. He's basically working on biomedical application. So I collaborated with him in this part, and somehow we able to create some good data from this. So we created some cortical screw and tried to improve the pull-out strength of the cortical screw. So what we did, we just changed the pattern, infill patterns, without changing the density of your infill density of your material. So trigonal, honeycomb, concentric, and gill. So what we observe, so these are the some tests which we, as we are like uh, time is getting, so because of lesser time, I'm just passing it in a uh, so just it's showing the cortical screw in the fixed jaw to find out and try to find out the pull-out strength. So we also calculate the compressive as well as tensile strength. So what we observe in honeycomb structure, we are getting higher strength. So try to find out why it is happening. What we try to analyze with the help of SCM, scanning electron microscopy, and see how the patterns look, and after the deformation how the patterns going to be look. So fractography is basically we used to do to find out why it is happening. So what we observe in fractography, there is a presence of cup and cone structure is there. In honeycomb, there is a brittle sudden failure is there. Because of this sudden failure, the overall strength is basically improved. So after that, we able to find out about to be 70% higher compressive, and 30 and honeycomb structure have approximately 17% higher compressive strength and 30% higher tensile strength than the other patterns. So uh, by we in this paper we just try to change the patterns of your 3D printing, and that improve the overall strength of our material. So the that's all. If you have any question, you are free to ask.
Dear participants, if you have any queries, please ask.
Thank you, sir. Very nice lecture. Can I ask you, sir?
Yeah, sure.
Can I have a question on that question on which you are telling about FEO, FE203, and FE304 on that time? I
Yes.
FE304 info, like a very polished sample, isn't it, sir?
What?
EBSD you have done of that sample of very polished sample which we have taken out FEO, FE203,
Yes,
FE304%.
yes, 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 yes.
Sir, I want to know actually one thing. Is it being possible to calculate the FEO, FE203, FE304 percentage in powdered sample also?
No. Powder, there should be there would be more heterogeneity will be there, no? So it will not be possible with the help of EBSD. Definitely, you can do with the help of XRD and those things. But with the help of EBSD, it will not be possible, because doing the EBSD of a powder, it's
Yes,
quite difficult, because
yes.
you are tilting it at 70-degree, and then you are placing a powder for longer time. So you are not going to get, and in powder, the heterogeneity will be there. So how, again, the question is, what is the size of your powder? You are talking about in 1 micron size or a 2 micron size, that is also going to impact, no?
30 to 100 microns around.
What?
30 to 100 microns around something.
30 to 100 micron. So
Yes.
it's going to be difficult. Like, because in ABS you can understand you are tilting it at 70 degree.
Yes, sir.
Okay, and then you are putting it for a longer run. So what you can do, you can take the powder, make it form of a pellet. Okay,
Yes.
center it or make it a form of pellet, and then try to find out that I do it. Or recently that one of my paper came in NECTA also, that what we did, we tried to work it in the opposite way, not in a oxidation, we reduce it. So what we used to have, we have a Fe2O3 powder, okay, made a pellet of that one, and then in hydrogen atmosphere we try to reduce it and change into Fe2O3 to Fe3O4, then Fe3O4 to FeO. Okay, then we'll trying to find out ki, like let's suppose if we put it a temperature of 500, then how much Fe2O3 convert into Fe3O4 for let's suppose 5 minutes, then 10 minutes, and 15 minutes, how that fraction is basically changing, or 200 degree or 300 degree. So that type of work we did. So to do that, we make it in the form of a pellet, then you can go for that.
Actually, sir,
Don't
I want to
powder
do
directly.
I want to do the comparison, something like that. Initially, that much amount of FeO, Fe2O3, Fe3O4 percentage are being there. Later on, after reduction or sample work, we got this much of oxides, or all the oxides have been removed, something like that.
That what in reduction of iron ore that we basically used in iron making processes. Okay, so what we used to do, we used to make it in a form of pellet. पाउडर में वो डिफिकल्ट हो जाएगा बहुत.
तो सर उसका टीएम से निकल जाएगा, क्योंकि ईबीएसडी में तो बहुत मुश्किल सा लग रहा है काफी.
हाँ, that's why I'm saying you go for the pellet one. That will be more appropriate way. Make it in a pellet, porous pellet रहेगा तो आपको रिडक्शन भी होगा तो वो भी इजीली पता लगेगा.
सिंटर करने से सर उसकी मतलब कंपोजिशन में डिफरेंस नहीं आएगा?
नहीं, that you have to optimize it. That can be done. आपको टेम्परेचर के साथ वो प्ले करना पड़ेगा. और आप नॉर्मल पैलेट फॉर्म में भी कर सकते हो ना, सिंटरिंग मत करो, नॉर्मल पैलेट फॉर्म में करो, हाई प्रेशर पैलेट्स फॉर्म में.
कोल्ड प्रेसिंग.
हाँ, कोल्ड प्रेसिंग से. आई एम नॉट सेइंग कि यूज इट फॉर हाई टेम्परेचर वन.
सर अपने इस पर टीएम का बात नहीं करा, आपने कहा था कि आप टीएम के रिगार्डिंग बात करने वाले
टीएम
थे.
का मैं ज्यादा इंक्लूड नहीं कर पाया, एक ही पार्ट लगाया है ये ब्राइट फील्ड इमेज का ही,
I think
क्योंकि
there was
अभी
a
भी ये
shortage
पूरा
of time is
कंप्लीट नहीं
also
हुआ.
there, na?
हाँ, वी ऑलरेडी लाइक more than 9.
Yes, sir.
You only asked me the bright field and dark field, na?
No, sir, I have not asked the bright field and dark field.
Okay.
That was
That was Dr. Shubham from Kanyakumari.
Okay.
so one more thing. How you are going to calculate it? There are very small grains and some are very, very big grains are there of FeO, Fe2O3. Then how are you calculating the exact percentage? This much amount of this thing are being present and this much. How we are justifying this thing through EBSD?
I'm not taking the average grain size.
Okay.
Okay. I'm bifurcating the phase wise.
Okay.
In EBSD, there is a way to take out one particular phase and make it in a different substructure, sub article. Okay. And then try to find out the grain size of that particular phase. Let's suppose, let's talk about this one. In this, I can choose only the magnetite one. Okay, others ferrite और वो सारा black में convert हो जाएगा. And then find out the grain size of magnetite.
Okay.
And then distinguish only the again make a subsheet and then remove the other phases and only make the subsheet of woostite, and then find out the grain size of woostite only. That can be done in EBSD.
इट मींस EBSD जस्टिफाई भी कर देता है सर कि कौन सा फेस मौजूद है वहां पर, FeO है, Fe2O3 है, Fe3O4 है, वो
Yes,
पूरा.
yes. But for the EBSD, you should have basic information. Like I will give you an example. Like when I was in IIT Bombay, so one user used to come. He's from NIT Jalandhar. I don't know right now where he's. So he used to bring two samples, which is one sample which is having copper as well as austenite phase. Okay, copper as well as austenitic stainless steel. Okay, and somehow he welded both the material. That is his uniqueness. How he welded, I have no idea. So he used to come there for the characterization part. So now the copper is having a lattice parameter around to be near to the same of which is having the lattice parameter of austenitic stainless steel, because both having a FCC structure. Copper is having FCC, and austenitic phase is also FCC, and the both the lattice parameter is same. So if I'm going to put for the analysis, EBSD analysis, कि मेरे को कॉपर भी चाहिए और ऑस्टेनेटिक स्टेनलेस स्टील भी चाहिए, तो सॉफ्टवेयर गेट कंफ्यूज, वो आपको कुछ भी नहीं देगा. Okay, so what you have to do, you have to go for then chi scan. आपने उसमें क्या करना है, EDS एनालिसिस भी करो, पैरेलली EBSD भी करो. तो आप फेराइट पार्ट को अलग कर लोगे, कॉपर को अलग कर लोगे, देन फाइंड आउट द ग्रेन साइज ऑफ एवरेज ग्रेन साइज ऑफ फेराइट एज वेल एज एवरेज ग्रेन साइज ऑफ कॉपर. मतलब फेराइट मीन टू से ऑस्टेनेटिक एज वेल एज कॉपर. सो फॉर द EBSD यू शुड नो कि विच फेज इज देयर. आपको पहले बेसिक अंडरस्टैंडिंग होना चाहिए कि मेरे मटेरियल में 4 फेजेस हो सकते हैं और इन चारों का लेटेस्ट पैरामीटर में इतना डिफरेंस है कि सॉफ्टवेयर का ओवरलैप नहीं होगा एक दूसरे के साथ. So there you can identify the phases quite easily.
I got it, sir. And in fact, I think I know that person also. I think he is right now in IPR, Gandhinagar.
Okay, so you can ask about those things.
Thank you, sir.
Okay.
Any other question?
सर मजा आ गया आज तो. हितेश सर, थैंक यू सो मच.
Thank you.
Dr.
Thank you.
Praveen, huh?
हाँ जी सर, थैंक यू सो मच सर, आप आए.
It's all effort of Dr. Praveen that Dr. Hitesh is there for this very beautiful session. Sir, आज आपके session को देख के ऐसे लगा कि you was a good teacher. Now you are in industry, but you have planned very well your talk. You started with the techniques and then you discussed with their results. I think it was a really very good talk. I think Dr. Rahul Sen wants to say something.
Thank you for giving me the opportunity.
Dr. Rahul.
No, sir. Anything actually. Thank you. I just asked the question. I just came here to
Okay.
say something like that.
Any other participants who wants to ask any question? So thank you very much, Dr. Hitesh, for this beautiful talk. And I think this is the time to end this. And
Thank you.
Thank you,
Thank you, sir. Thank you. Thank you.
Thank you.